while I want to give a lecture on double integrals, I'm being derailed into talking about fun things like gradients. There we go. A gradient is fun, but we're talking about gradient for 2 days. I want to talk about something different fun. Okay, so your gradient, and so that is confusing, okay, because so the sentence I just started saying before I recorded was, in single variable calculus, you're dealing with so few dimensions that concepts that are actually different from one another actually get conflated because you lose dimensions in shrinking down into single variable stuff. So back in single variable calculus, here's a curve, and you work out that, and you'd say, okay, well, that's the slope of you'd work out this grade. Let's have a look. That's f of x, and here's a, and then we would say the slope of this is f dash of a, which is fine, and we'd still say that, except we wouldn't put a dash. We'd talk about x derivatives and y derivatives. But then we'd say the gradient of that line is the slope, okay? And gradient and slope, we only saw gradient in the context of a straight line. Y equals mx plus c. Here's a nice straight line, and the m is the slope of that. Sorry, this is scruffy writing. And in straight lines, and not even straight lines in space, straight lines in R2, then slope and gradient were the same thing. But no longer. Okay, slope and gradient are no longer the same thing. Slope is a number. Now, back in yesterday's tutorial, some of you are still doing the tutorial today, you'll see a lot of the questions talk about rate of change. Same thing here, rate of change. Which I know bothered some of you because, of course, in physics, rate of change inevitably means rate with respect to time. But in the context, if you just have some function of x and y, rate of change just simply means rate of change with respect to the independent variable, whatever the independent variable happens to be, frequently x and y. Okay, so rate of change, slope, derivative, directional derivative, these are all just different words for the same sort of stuff. Scalars, numbers, cluster them together into a vector and you get a gradient vector. Okay, and then I can talk about orthogonality and stuff as well, yeah?
That gradient vector, that's grad f, right?
That's grad f. So grad, of course, just being short for gradient. So sometimes we'll say what's grad f, sometimes we'll say what's the gradient of f, same thing. Grad, gradient, vector, okay? Gradient is a vector. All right, and then grad f turns out to have some very nice little geometric properties. Okay, I'm going to give that same old picture that I've been giving for the last couple of days. Let's say you've got some surface, okay, and we've got level curves, and here I'm drawing them as contour lines on the actual surface. We can draw those level curves. Let's have a look. How many are there? There's a dot. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There we go. There's y. There's x. Okay, if I were trying to do a good job, I would make sure that because this is a paraboloid, the outside circles would be closer to one another than the inside circles. If I were trying to do a good job of my level curves, I would label them k equals 0, k equals 1, k whatever. I'm not trying to do a good job right now. I'm just trying to talk about grad. So let's have a look. Let's mix things up. I've always been in the first quadrant. Let's be in the fourth quadrant. Here we go. Little ant standing on the surface over there. If I project that point down onto here, it'll be somewhere over there. There we go. There's that dot projected down onto the xy plane. Okay. If I express this function as z equals f of xy, and I work out grad of f at this point here, let's have a look. That's a, b, c. If I work out grad of f at a, b, I'll get a two-component vector because z is a function of two variables. I'll work out an x derivative, a y derivative. I'll have a two-component vector, and I can draw that onto my diagram, onto my level curves diagram, onto my 2D diagram, and that little black arrow will have two very important geometric properties. One is that it points in the direction of greatest slope, the direction of greatest rate of change, the direction of greatest directional derivative. It points uphill as steeply as it can. Also, it's orthogonal to the level curve. Okay? However, I chose to take my z across the equal sign and actually get 0 equals f of xy minus z, or the other way around. I could take the f across to the z side, it doesn't matter. And let's say I decide to call this function f of xyz, and I work out grad of big F. Grad of big F is going to be a 3-component function, because big F is a function of 3 variables, x, y, and z. And if I evaluate it at a, b, c, I'm going to get a 3-component vector. Question at the back there?
How do you know that it's pointing in the direction of the latest?
We derived that with that dot product thing. That mod f mod u cos theta story, where we said that if you want to maximize your directional derivative, you require theta to be 0. Geometrically, what that means is that your greatest rate of change is in the direction of u if u is pointing the same way as grad f, because theta is 0, the angle between them is 0. So now, if you choose to do that, you now get a 3-component vector. You can't draw that onto your 2D picture. You have to draw it onto your 3D picture, and it will point, sorry, it doesn't really look like it on the picture, but it'll point orthogonally out of your surface. It'll be like you take a pin cushion and you put a pin in. Okay, it'll look like that. It'll look like a pin, a spike, pointing orthogonally out of your surface. Okay? You can still interpret that grad as a greatest rate of change, but it becomes very metaphysical, because in the 2D case, if you move in the direction of that arrow, you will, in the 3D world, be moving most steeply uphill. Okay? Because these are the level curves of a 3-dimensional surface. If you want to interpret that black arrow in the same geometric way, you have to think of this surface as being the level surface of a 4-dimensional function. And if you move in the direction of that black arrow, you will be moving at greatest rate of change from this level surface to, if you will, the next level surface of that 4-dimensional function. We don't deal with 4-dimensional functions in this course because engineers prefer reality, but you still can interpret it that way. And in fact, one of your TUT questions does actually encourage you to think like that, to think in terms of level surfaces. But don't worry about that. Don't worry about that. If we want you to talk about grads and greatest rate of change in the same sentence, we won't be talking about arrows like that. We'll be talking about arrows like this. Yes, can I do double integrals? Yes?
The gradient function is always 1 dimension less than the original function.
Your gradient function, yes, okay, so the question is your gradient function, or at least asking for clarification, the grad function is 1 dimension less than the original function. Yeah, in a sense, because this 3-dimensional grad down there is the grad of big F, where big F, of course, has got 3 variables on this side and presumably 1 on that side as well. So yes. Because you're always differentiating something with respect to whatever. So if you're differentiating with respect to 3 variables, then there's the 4th something, that's the thing you're differentiating with respect to. Okay, so that's grad. And I'm doing double integrals, otherwise we're going to end up 2 lectures behind. Yes, yay! Double integrals. Double integrals. Let's talk about double integrals. Where are my notes? Okay, so first of all I want to give you a comment that's intended to comfort you, which is you only ever integrate with respect to 1 variable at a time. Okay? Just like you only ever differentiate with respect to 1 variable at a time. Okay? Double integrals are actually, I really mean this is not me being, sometimes people can say, oh, such and such, that's so easy, when in fact you know it isn't. But double integrals really are easy. Surface integrals are tricky. But double integrals, once you've got the hang of them, they really are easy. If you see a double integral in an exam, you go, hooray, I've got an easy question, I'm going to get 4 marks for this one. Okay, double integrals really are not very tricky. The trickiness does come in surface integrals, where you need to have had your per neutron. Okay, here we go. Double integrals. First of all, a little bit of writing before I jump into examples. The double integral. Okay, here we go. Here's some notation. All right. I'm putting an R there at the bottom of those two integral signs, which means I'm integrating over some region, which I'm calling R. My integrand will be a function of 2 variables. And instead of putting a dx here or a dy here, I'm putting a d capital A, where that A stands for a little piece of area of my region R. Okay, so this double integral can be interpreted as the volume. Okay, so later on we're going to do applications of double integrals, and volume is going to be one of those applications. But if we actually start off even thinking of the definition of double integrals as being volumes, it helps us understand what's going on, in the same way as thinking of single variable integrals as being areas. The volume of the solid that lies between f of xy, if f is greater or equal to 0 over r, and the xy plane. I'm going to draw some pictures so you'll see what I mean. Over the region R, an area in R2. Okay, and we define our double integral f of xy dA to be the limit as m and n tend to infinity of this. There's 2 sigmas, I going from 1 to m, I going from 1 to n, f of xi, yi, delta a. Okay, let me do some pictures to show you what I mean by all of that. And I'll give you an analogy with single variable calculus. Okay, in single variable calculus, oh, someone's calling. Don't answer that. You're in a math class. Okay, so all right, so that looks a little bit, I think the wind's blowing on that one, okay? But you remember pictures like that. Back in single variable calculus, we would say the integral from a to b, here's a, here's b, the integral from a to b of f of x dx is the limit as n tends to infinity of the sum of f of xi dx, sorry, delta x, I going from 1 to n. Okay, look familiar? So we had this curve, and we want to know the area under the curve. So we chop the area up into rectangles, and we work out the area of the rectangles. And the area of every rectangle is length times breadth. The length is f of xi, and the breadth is delta x. We add up all such areas, and then we say, it's almost like a thought experiment. We say, well, what would this area become if we allowed the number of rectangles to tend to infinity and their width to tend to 0? And that is what we defined as the integral, which was defined as an area under the curve. That definition still holds, even if it's not strictly speaking an area, because if your curve is underneath the x-axis, your function values will be negative. You'll actually get a negative integral, and that's fine. But you can no longer strictly interpret it as an area, because areas are positive. Similarly, if your curve is above in some places and then dips below in other places, you actually end up almost with a sort of a cancelling out. And once again, it's not strictly interpretable as an area, but it's a good start. Okay, so you chop it up into rectangles. We're going to do the same thing now. We're just going to increase by a dimension, and instead of having these flat rectangles, we're going to have sort of rectangular pillars. Okay. So what if we have some piece of surface? Here we've got some piece of surface floating in the air, and what we're going to do is we're going to divide up okay, so this down here That's my R. That's my region in the XY plane. This is my R, which I'm going to chop up into lots of little blocks like this. Okay? And I'm going to have kind of pillars. Let's have a look. Yeah, I don't want to put too much detail onto the picture because then it stops being sort of, you stop seeing exactly what it's meaning. But let me maybe draw in one. Oops, not great. But we're going to chop it up into lots of pillars, okay? So each little box here is delta x, it's delta A equals delta x times delta y, okay? And I'm going to have, I had two i's here. Do I want I? No, I actually want j. I'm going to go back to this formula. I made a little mistake in this formula. I've got xi, yi. I'm actually wanting xi, yj. And it's j that's going from 1, which one do I want? Doesn't really matter. J going from 1 to n. I apologize. We need to number the x's and the y's differently because we might have a different number of them. So we need to number them differently. Okay, so hopefully that's not too problematic. We're chopping up our region into lots of little blocks. And we're thinking of a sort of a pillar going up from each block until it bumps into the surface. And instead of summing up the areas of a bunch of rectangles, we're going to be summing up the volumes of a bunch of pillars. Okay? And that's what that double sigma is at the top there. Because once again, you've got the height of your pillar, which will be your function value, but then times by the cross-sectional area, which is delta A. Okay? But instead of having to sum up across x's, we're going to have to sum up across x's and y's, which is why we need two sigmas. But once again, we want the number of divisions to tend to infinity along the x dimension and the y dimension. So that's a rather intimidating looking formula at the top, but it's really just adding in another dimension to this very familiar concept from single variable calculus. Yes?
Is this all with z being fixed over the whole region?
Z will not be fixed. Z will be changing across the region, and Z, of course, is signified by the f of xy. So in my picture, it looks fairly flat, but it could be doing all sorts of things. Now, once again, just like integrals and areas, once your curve goes below the x-axis, your integral is not strictly interpretable as area. The same thing applies here. If your surface is below the xy plane, or if it's somewhere above and somewhere below, then it's not strictly speaking correct to equate volume and double integral. But it does as a good start. Integrals can always be negative. Single integrals, double integrals, triple integrals, they can always be negative. Okay, triple integrals can be negative, yes, depending what it is that they're measuring. We often use triple integrals to measure volume or mass, in which case negative result would be a bit fishy. But I suppose it depends what you're measuring. Okay. All right, one more sentence, but it's really already in the diagram. In the double Riemann sum, that's that thing with the sigmas in it. The area R has been divided into n by m rectangles of area delta A equals delta x times delta y. Now, of course, if your region is not rectangular, it means around the edges, you kind of, you'll be missing bits around the edges. But remember, we're allowing, the number of little rectangles, if you will, to tend to infinity, and their delta x and delta y to tend to 0. So even sort of a wiggly perimeter of your region will end up being accommodated by that limit. Okay, there are some properties of double integrals, which I suppose we need to get out of the way before doing some examples, but you'll find that the properties of double integrals are exactly the same as the properties of single integrals, and so they're not surprising, and in fact you'll find yourself taking them for granted. Properties of double integrals. Number 1. The double integral of a sum is the sum of the double integrals. Okay, that's something we could do with single integrals, and in fact it is something we can do. Now these properties are things that can be proven. You would take the definition of the double integrals with that Riemann sum and you would prove that this statement here is true. So properties are not things that we just assume or some things that we define. Properties are things that we can prove. But I'm giving them without proof. But you probably did prove some of your integral properties back in first year. Did you? Maybe. If you have a constant multiplied by your function, you can pull that constant outside the double integral. Again, hardly a surprise because you do this for single variable integrals rather. Number 3, what have we got here? If we have one function f which is bigger than some other function g all over your region, so for all x, y in R, then the double integral of the bigger function is going to be larger than the double integral of the other function. Again, hardly a surprise. If we have one surface that's higher up in the air than the other surface, we expect the higher one to have more volume underneath it than the one that's lower down. This becomes a slightly less obvious property when your surfaces are not above the x-axis but are below or a mixture, but the property still applies. Okay, so dA we replace with dx dy or with dy dx. It represents that that's delta A, here we got delta x, here we got delta y. So the d, up before I've been writing delta x and delta y, but of course they become dx and dy in the limit as delta x and delta y tend to 0. And the limits of integration are chosen to describe R. Okay. Let's do some examples. Handbook. Yay, chapter 2. Okay, all right. I'm going to do an example, but first of all, let me talk about that little note that I've got just at the top of page 41 on integration terminology. Now, if I write an integral, so let me just change color here for a bit. If I write this, I would call that a double integral, okay? That's fine. If I write, let me give it a gap. If I actually have limits of integration written onto my integral sign, like 1 and 2 and 3 and 4 of x squared y dx dy, or in fact, let me not even put a function in there. Let me actually still leave it as f of xy, just to show you what it is I'm getting at. If we actually have limits of integration written in, then you can still call it a double integral, still double integral, but you can also call it, what's the term there? Repeated integral or iterated integral. Iterative? Iterated. Iterated integral. I think your textbook tends to use the term iterated. I think it's your textbook that tends to use the word iterated, and but historic notes from this course and old tutorials and things that you run across tend to use the word repeated to mean the same thing. Okay, so it simply signifies that you're actually ready to do the integral because your limits of integration are there. Repeated seems like an odd name. Iterated I could understand because you do your integration iteratively. In this particular case, you do x first and then y. But I just want to introduce you to that term. Okay, you're going to see that term repeated integral. You're going to see the term iterated integral. It simply means a double integral that's got its limits of integration already put into the expression. Okay, that top form, which doesn't have the limits of integration in yet, you can only call a double integral. Okay, so that's just a language issue. Yes?
The R, is that representing, because now you put the R in the...
No, I didn't. The 3, 4, and the 1, 2 are now describing R. Yeah. Okay, alrighty then, let's do some examples. Yay! Number 1. No, somebody yawned. Don't yawn. Unless that was a kind of waking up kind of yawn rather than a going to sleep kind of yawn. Here we go. Okay, there we go. We've been given a double integral. The integrand has got y's and x's in it, and R has been described. R goes from, okay, somebody's calling me, but it's not my children. Well, not that my children have phones, much to their distress. No. I'm going to assume it's got nothing to do with my children. If it's Linda calling, she knows where to find me. Okay, all right. Okay, so I've been given my region. X goes from 1 to 2, and y goes from 0 to pi. That's my region. Okay, if you read the question gives it to you. It says, let me write it down. What does it say? It says x is between 1 and 2, and y is between 0 and pi. Okay, your region has to be described to you in some way. Either like that, or with a picture, or with words saying something like the region that's bounded by y equals x squared and y equals x, or something like that. Somehow your region has to be described to you. Okay? Always draw a picture. Always draw a picture. Always draw a picture. Okay, what are you going to do? Excellent, thank you very much. But only about a quarter of the class actually said that. The other 3/4 are also going to draw a picture. Okay, all right. Okay, you're going to draw a picture primarily because it's really helpful. But if really helpful isn't good enough for you, you're going to draw a picture because you get marks for drawing the picture, okay? So if helping yourself is not sufficient motivation, getting marks perhaps is, all right? Even if the question doesn't say, please include a picture, draw a picture. Okay, all right, moving on. Let's actually integrate this thing. Okay, so the next step, let me call that I. There we go. The next step is to figure out or to decide which variable we're going to integrate with respect to first. Now, just like with differentiation, when you differentiate with respect to one variable, you hold the other variables constant. Same with integrating. When you integrate with respect to one variable, you pretend all other variables are constant for now. Okay. Somebody's saying do x first. I agree. I agree that x is a good choice. Okay. So now you have to say to yourself, what did I differentiate? Now with integration, with single variable integration, you kind of, whenever you integrate, whenever you anti-differentiate, you're saying to yourself, what did I differentiate to get this integrand? Now you have to add in some more words. You have to say, what did I integrate with respect to x to get this integrand? If we wanted to do y first, we'd have to say, what did I differentiate with respect to y to get this integrand? Sometimes your region strongly recommends that you do one variable for the other. Our region is a rectangle. It's as ordinary as you can get. our region couldn't care less which one goes first. Sometimes your integrand strongly recommends which one you do first. Sometimes it really doesn't matter. I'm going to do x first and then y. Okay. Now, the way the integral signs work is they're kind of clustered like sort of layers of an onion. Because the dx is going first, the dx is on the inside, and the limits of integration will be the inside integral. X goes from 1 to 2. The y is going last. It's written on the outside. The outside integral sign is the y, belongs to y. It goes from 0 to pi. So I asked myself, what did I differentiate with respect to x to get that integrand? And the answer is going to be minus cos xy. xy. That's right. Keep putting in funny symbols there that don't belong. There we go. xy. dy. Oh dear, someone's sneezing. Bless you. Okay, so let's think about that for a second. If we were going to differentiate minus cos xy, we would have to use some chain rule. And we'd say the derivative of minus cos xy is positive sine xy times by the derivative of xy, which is y. Just like in single variable calculus, if you're bad at differentiation, you're going to be worse at integration. In order to be good at integrating, you've got to be good at differentiating. Because if you ask yourself, what did I differentiate to get this, and you don't know your differentiation rules, you're not going to be able to answer that question. So, I hope you agree with that. Now I'm going to plug the 2 and the 1 in, and the 2 and the 1 are going to get plugged into x, of course. So that's minus cos 2y plus cos y. And now, it looks like a problem I could have had in first year, because now I've only got one variable left. Now it's a single variable integral. And I asked myself, what did I differentiate to get that? And it'll be minus a half sine 2y plus sine y from 0 to pi. Sine of 2 pi is 0, sine of y of pi is 0, sine of 0. Okay, all right, there we go. So if all of this just disappeared and I gave you something a lot like that, would you be able to do it? And if the answer is no, why not? Which was the bit that you know you would have got stuck on? Choosing which one to go first. Yeah, that is a sticky thing. A question over there? What happened to the y? The y that's sitting in front. I recognize that y as being a byproduct in a sense of chain rule when I differentiate it. I've got an xy inside the sign, and I've got a y outside, and I've done enough chain rule to know that I end up with that sort of pattern when I've carried out chain rule on something that looks like sine xy. If I differentiate cos xy, well, minus cos xy, if I differentiate minus cos xy, chain rule says I have to differentiate the outside function first, so I'll get sine xy. But then I still need to multiply by the derivative of the inside function, so I need to multiply by y. And that's the story of that y. That y is the consequence of carrying out chain rule on that thing over there. And it's recognizing that, it's looking at that and going, haha, that looks an awful lot like chain rule. That helps us choose to do x first. But of course that only happens if you've done a whole bunch of chain rule and you're just used to recognizing it. Question over there. What's it representing? Okay, so what it's representing, so the question is, what is this integral representing? It's representing the cumulative effect of whatever that integrand is across our region. If we want to think of it as volume, like we define double integrals to be, that surface over there must be partially on top of the, above the xy plane and partially below the xy plane, and that's why we're ending up getting 0, because the volume above and the volume below are cancelling out. Yeah, there's not a lot of physical things that take on negative values and hence can cancel out, so I'm struggling to think of examples. But in a general sense, what it's measuring is the cumulative effect of that integrand across our region. Because sometimes what double integrals represent is not volumes. Sometimes in double integrals we think of that region as being a lamina. We think of it as actually being a two-dimensional object. And we're trying to measure some quality of that two-dimensional object, where it could be the mass of the lamina, or it could be the sort of charge density, not the charge density, the total charge of that's present on the lamina. I'm struggling to think of examples, but some sort of quality of the lamina that we calculate by basically summing up some cumulative effect of whatever that integrand represents. Question?
Ma'am, so now we have zeros on, does that mean that this thing has no volume?
It means that this, if we were going to draw this, so hold on, let me even say that. Let me just, the 0, yes. If volume, then it means, because an integral isn't actually a volume. An integral is only a volume if your surface is entirely above your xy plane. It means equal parts above and below the x-axis. Not x-axis, xy plane. So if it was some sort of surface that, if our surface did this sort of thing, if it did that sort of thing where that sort of dotted bit there is trying to show where it's passing through the xy plane, I should actually try and figure out what that surface actually looks like. It can't be that hard. I'd have to think about it for a second. But if it looks something like that, where part of it is above the xy plane and part of it is below, then the volume above, the true volume above and below are cancelling out and giving me a total integral of 0. Not a volume of 0, an integral of 0. Okay, all right, but that's the end of the lecture. I'll do a couple more, I'll do one more on Tuesday, yeah?
On the volume of that,
You'd have to figure out where that chopping through the xy plane happened, and then you'd have to do 2 separate integrals, and you wouldn't put absolute value to just do 2 separate integrals. Okay, I'll stop there.